Let's have a look at question 34 in this video. So Domino's Pizza advertises that they deliver pizza within 15 minutes from an order. A sample of 25 customers is selected at random. The average delivery time in that sample was 13 minutes and 40 seconds with a sample standard deviation of 4 minutes. Now we assume that the times are normally distributed, so we want to test whether the population mean is less than 15 minutes, and these are the following hypotheses. Now we're gonna reject the hypothesis or not. That's what we're looking for. So before going further, let's have a look at the data over here. I wrote them on the right. We have the population mean, we have the sample mean, which is 13.67 because 40 seconds is 2/3 of a minute. 13 minutes and 40 seconds is 13 minutes and 2/3. 2/3 is the same as 0.67, so 13.67 minutes. The sample standard deviation is 4 minutes, and we have 25 observations. Now, we have a small sample. We have a small sample of 25 observations only, and we are given the sample data. We have the sample standard deviation, and we have sample standard deviation, meaning that we're going to use the t-test. The t-test has the same analogy as the z-test. So we're comparing how much does this sample mean differ from the population mean in terms of standard errors, but we're having different critical values because the sample size is smaller, and we have to take that into account. So let's actually calculate the t-test and see what conclusion we're going to give. So as we just said, the t-test is the same logic as the z-test. We're comparing the difference from the sample mean from the population mean relative to the standard error, which is the standard deviation divided by square root of n. So if we calculate the t-test in this case, we're going to get the difference between 13.67 minus 15 minutes divided by the sample standard deviation of 4 relative to the square root of the number of observations, square root of 25, and that's equal to minus 1.675, minus 1.675. Now, just like with any other test, to give a conclusion, we must compare it with the critical value. So we're going to look at the distribution of the t values, the t critical values. Now, the degrees of freedom is going to be n minus 1 at this 5% significance level, 5% significance level, and we can see that the alternative is one-sided. The mean is less than 15, so the only tail of rejection region that we can have will be the left tail, meaning that 5% probability must be on the left tail only, with the degrees of freedom of n minus 1. So that's the critical value t of 5% significance level. N is 25 minus 1 is 24. If we look it up in the table, that's equal to 1.711. So let's draw this on our t distribution. So we're going to draw the t distribution here below. We're going to draw the t distribution here below. Here we have it, the t distribution. It's a normal distribution. We're having the rejection region, the critical value 1.711, 1.711. This is going to be a rejection region, but recall that the t distribution is symmetric around the mean of 0, around the mean of 0. So we also have a negative critical value on this side, minus 1.711. This is going to be another critical value over here, and because the test is one-sided, we're interested in this region only, so we're looking at the left tail. Now our value that we calculated in the test is equal to minus 1.675. So if we plot it on our t distribution, minus 1.675 would be somewhere over here, and we can see that it is not in the rejection region, so we do not reject the null hypothesis. We do not reject the null hypothesis, which means that the average delivery time is not significantly less than 15. So the average delivery time of the pizza is not significantly smaller than 15. So what that means is that the observation for our sample that we found, the mean for our sample that we found of 13.67 minutes, most likely happened by chance. It's not large enough to claim that the actual population mean is less than 15. I hope this makes sense, and we are done.